All right, today we're going to begin Module 9, and we're going to start looking at exponential functions here in the first section. So really what we're going to do is look at the graphs and what makes an exponential function behave the way it does, some things that we can predict by looking at the equation and how we can convert that into graphs. So first of all, when you look at exponential functions, it's described in a certain form, and y equals a times b to the x is that form, where a is not equal to 0, b is greater than 0, and b is also not 1. Okay, and as you look at that, what you need to see, a and b are numbers. The variable is x, so your exponent is the variable. So y times a times, or excuse me, y equals a times b to the x, or this will be f of x equals a times b to the x. This is the general form. I'm going to show you some examples of where maybe the a is a 1, so you don't really see it, or b could be a fraction or a whole number. So we'll look at how that plays out. When you look at these exponential functions graphically, they behave a certain way. Okay, first of all, they don't move at a constant rate. A constant rate of change is a line. It moves, over and up consistently, which is your slope. Okay, an exponential function does not behave that way. It actually has a common ratio, and that common ratio is the rate of change, and it increases by a scale by the same factor each time, like it doubles each time or it triples each time or something along that lines. So it's moving using the same scale factor, but it's not a constant rate of change like your function is. So let me show you an example of that here. All right. So you see two graphs here. The one I'm kind of tracing, this is exponential, and they got a y equals 2 to the x power. The other graph here is the line y equals x. All right, y equals x is linear, and that's what we're focusing on here is linear. And what we're showing you here is this linear equation when graph makes a straight line, and the rate of change is constant. Over 2, up 2, over 2, up 2, over 2, up 2. So that's a consistent rate of change that makes it a straight line. Now we look at the same graph, but now focus on the exponential equation, which is y equals 2 to the x power. Now the rate of change isn't constant, but it is changing by the same factor. So if you look at this, this is over 1, up 1, over 1, up 2, over 1, up 4, over 1, up 8. So we're doubling it each time. We're doubling the next output number is doubled. So that's where you see an exponential curve. An exponential curve looks like this. Okay. And the interesting part is as this exponential curve is coming down and crosses the y-axis and starts going over here in the second quadrant, it's getting closer and closer to 0, but it actually will never touch. It'll just get very, very, very close, and it'll just keep hugging that line and getting closer and closer, but never actually touching. Okay, that's what an exponential curve does. Okay, now how do we identify exponential behavior? Well, here's an example of the Richter scale, and the Richter scale is measures the energy released by an earthquake and assigns it a magnitude. These orders of magnitude are approximated by comparing them to explosive power of TNT, that's dynamite. Determine if this represents exponential behavior. So what we're going to do is analyze the change in the TNT for each change in magnitude. Okay. So for example, a magnitude of 1 is 0.6. A magnitude of 2 is 6. So as I look at the change here from 0.6 to 6, that's multiplying this by 10. Okay. The magnitude of 3 is 60. What's the change from from magnitude of 2 to 3? Well, we multiply that by 10. Okay. Magnitude of 4 is 600 from over here. 60 to 600, multiply by 10. Magnitude of 5 is 6,000. 600 times 10 is 6,000. So this isn't changing at a constant rate. It's not going up 5 each time or up 10 each time. It's changing by a multiple of 10 each time. Okay. So since this change increases at the same factor, a factor of 10, we're multiplying by 10 each time, given every equal change in magnitude, up 1 times 10, up 1 times 10, up 1 times 10. This then, therefore, is an exponential behavior. This represents exponential behavior. We could write an exponential equation to represent this particular graph or this particular set of data. Okay. Okay, now when it comes to exponential functions, there's two different types that we look at. And we'll do a lot of these coming up, but right now we just want to get the basic idea down. Okay. There's two types. One is exponential growth. Okay. Exponential growth is modeled this way. Y equals a times b to the x. A is not 0. Now, this is the big difference. B is greater than 1. So the base number of our exponent here, which is x, this base number b has got to be bigger than 1. Okay. When this base number is bigger than 1, doesn't matter what a is. When b is bigger than 1, it's exponential growth. So for example, this y equals 2 times 3 to the x, because the base of the x is 3, this is growth. The a, we'll multiply our answers by 2 when we're done doing this exponent, but the bottom line is we're looking right here at b. An example of exponential growth is this. Now, this example is not necessarily this graph, but all exponential growth is going to go like this. Now, there's some characteristics of this. As soon as I know it's exponential growth, okay, I know the graph roughly is going to look like this. We'll piece it together, but we know it looks like this in general. And then we know some other things. The domain is all real numbers. Domain are your x's, your inputs. And you can input any number you want along this x-axis, either direction, and you'll get an answer. The range are numbers, y values greater than 0. Notice that, remember we talked, we'd never go below 0 on the number line as far as answers go. This curve comes down and gets really, really, really close to 0, but it never touches. Okay, so therefore you'll never get an answer of 0. So all of our answers will be bigger than 0. The intercepts, we're always going to have one y-intercept. We're going to cross the y-axis during this exponential curve. We're working our way down. We'll never cross the x-axis, so there'll never be an x-intercept. End behavior. Okay, so the way you look at this is if you start at 0, as x values increase, so as I'm inputting numbers for x going to the right, the answers, the f of x's, are going up. This could be a y or f of x. So as x increases, our outputs increase. Whether you want to call it f of x or y, doesn't matter. As x gets bigger, the outputs get bigger. They go up. As x decreases, so it's starting at 0 and going to the left now, as I'm putting in numbers for x in a decreasing fashion, the answers here are getting closer and closer to 0, but they don't touch. Okay, so that's what all that means. And that happens for every exponential growth graph function. Okay, the other part of this is exponential decay. Okay, now so these equations look exactly the same. Y equals a times b to the x. Here's your difference. Your b has to be a number between 0 and 1. Between 0, can't be 1, can't be 0. It's got to be somewhere between. So a fraction or a decimal between 0 and 1. Okay, so when this b is between 0 and 1, I got a decay curve. Okay, so here's an example of a exponential decay function. Again, this y could be f of x, g of x, could be either a y or a function notation. This is what every exponential decay kind of looks like. So the graph is going to start, it's going to be increasing as you go to the left up, and as you come down to the right, it's going to swoop down here. It's going to cross the y-axis. It's going to come to the right, get closer and closer and closer to 0, but it's never going to get there. It's going to kind of, it's the mirror image of exponential growth. Now we're just coming the other way. So what are some things that we know? Number one, domain the same, all real numbers. You can put any number in for x you want, and you will get an answer to the equation or to the function. The ranges are the same. All of our answers, which are our y values, are going to be above the x-axis. We're never going to cross the x-axis. So all of our answers are up here. So the answers are all going to be greater than 0. Again, one y-intercept, no x-intercepts. We're never going to cross the x-axis. And behavior, as you look at it now, what happens as we start at 0 and go to the right? Well, our answers are getting closer and closer to 0. As we start at 0 and put in x's going to the left, our answers are getting bigger. So as x increases, the function approaches 0. It's getting really, really close to 0. As x decreases, or we're inputting numbers that are less than 0, our function answers are actually getting bigger. Okay, there's one last thing to talk about. I didn't give you any of these tonight in homework, but it's called an asymptote. An asymptote is a line that the graph approaches. So in both of these two cases, we have a horizontal asymptote at y equals 0. Y equals 0 is the x-axis. Okay, and it's an asymptote because as we come down, we get closer and closer and closer to y equals 0, which is the x-axis, but we never touch. Whether it's growth or decay, that happens. Okay, looking at your homework tonight, you're going to kind of get questions like this. Now, you're going to be asked to graph, and there's a graphing function included in the Alex assignment. Your homework is on Alex. But essentially, it's making a chart, a table of values, and then plotting your points. Okay, so this is our first one that we're going to graph. Graph it, plot 5 points on the graph of the function. Guys, you need to make a table of values and calculate. Now, what kind is this? Is this growth or is this decay? Well, our b, which is the number that is the base of the exponent x, is a number between 0 and 1, so we're looking at decay. So we know if I jump over here to the graph, I know it's going to go something like this. That's what decay does. Okay, it's up here in the second quadrant. It kind of swoops down on a curve, crosses the x or y-axis, and gets really close to the 0. All right, so what we're going to do is we're going to load in some numbers. Here's my x values. Here are my function values, f of x. Remember, f of x, y, same thing. All right, now what we're going to do is I preset that I'm going to choose -2, -1, 0, 1, and 2. You can choose, you can have a little variation here. Is fine. Don't get too crazy. Stick right around in here with your input values, but we're going to just calculate it. So f of -2 would be 1/4 to the -2nd power. Now be careful when you put that in your calculators. Make sure you're grouping things correctly and you're using the negative symbol, not the minus sign and so forth. But you guys know how to do negative exponents. Okay, the answer to this is 16. Okay, and then f of -1 is 1/4 to the -1 power. That's 4. Okay, f of 0, anything to the 0 power equals 1. F of 1, 1/4 to the 1 power to the first power is 0.25, or 1/4 if you want to write a fraction. Okay, f of 2 is 1/4 to the second power. That's actually 0.0625. That's 1/16 if you want to write a fraction. So input, output, input, output, input, output, all the way down through. These are ordered pairs. So I'm going to plot my points. -216 is actually up here. I didn't have my graph big enough, somewhere up in here. Okay, -1, 4, 0, 1, 1.25. So that's right down here to 4th. 2 is 0.0625. And you can see how fast we're getting closer to this y, or closer to the x-axis. But look at the curve. I don't have the ability on this page to put a good curve in for you. But what we do is just connect the dots. So we're going to bring it down. We're going to start to curve along, and don't go below the x-axis, because this graph does not go below the x-axis. It hugs this line. Remember, this would be my asymptote if I drew one in. Okay, but that's graphing a exponential decay function. Okay, another one, same question type. Now we're looking at this as our given exponential function. The base of the x is 2. That represents exponential growth. If b is bigger than 1, this is growth. So I know over here, if I were to look, just kind of sketching a graph, it's going to go something like this. Okay, that's exponential growth. Now let's put a table of values together. I chose the same ones. Okay, I'm going to go through the same process. F of -2 is 3 times 2 to the -2nd. Remember, 2 is being raised to the -2nd, and then we're multiplying our answer by 3. Okay, so don't do 3 times 2 to the -2nd. That's not correct. You want to do 2 to the -2nd, multiply your answer by 3. That is 0.75. F of -1 is 3 times 2 to the -1st. 2 to the -1st times 3, 1.5. F of 0, 2 to the 0 power is 1. 1 times 3 is 3. F of 1, 2 to the 1st is 2, times 3 is 6. F of 2, 2 squared is 4, times 3 is 12. So there's my input outputs. Here are my ordered pairs. This should, when we plot this points, represent an exponential growth curve. Okay, -2, 0.75, -1, 1.5, 0, 3, 1, 6, 2, 12. So again, we're going to hug that line and we're going to curve and go up. All right, so that's graphing exponential functions. You do the same process, whether it's growth or decay, but you should know before time what it is by looking at that B. Okay, so we'll get some paper out, plot these points, make sure you can input, output, find the values correctly, make sure you can sketch the graph. Okay, all right, so there's more information on this on the McGraw-Hill site under lesson 9.1. The homework tonight is on Alex. Make sure you're getting that done. Write things out so that you can see them, input things into calculators correctly, and make sure you plot those points correctly.